connected to this computer. There we go. Okay, this way it'll be on the Blackboard so that you can reference this later when you need to write these lab reports. Okay, so just for the sake of the recording, we're talking about doing a second order fit to the virial equation for pressure versus compressibility data. So if we extend our compressibility data from last time up to higher pressures, we can see some curvature in the data. And so we're going to fit this to a quadratic equation of the form that's shown over here. Okay, so sorry about that. So now I'm going to select this data and I'm going to go to add trend line. And let me bring this window over so that we can see everything. Okay, so the default is to add a linear trend line. But in this case, we don't want a linear trend line. We want a quadratic polynomial. So I'm going to select polynomial. And we want a polynomial of order 2, which is the default. So I can leave this default setting the way it is. And you can see that now the line turned into a quadratic curve. If I want to see what the best fit parameters are, the easiest way to do that is to display the equation on the chart. I can also display the R² value on the chart if you want. I'll put this equation up here. Maybe this is a little bit too small to see, so I'll make it bigger. So I'll increase the font size so it's a little bit easier to read. And maybe we want a little bit better than 1 digit of precision. So I'm also going to change the format that Excel uses to display these numbers. So I'm going to left click on this box here that displays the equation. I'm going to go to format the trend line label. And okay, that brings up this window over here. And so there's a couple different options. I could say I want to display numbers with a certain number of decimal places. Maybe this is good enough for our purposes right now. Not really, right? Because this first number, now it only has 1 digit of precision. So maybe the better way to do this would be to put it in scientific notation with a lot of decimal places. That way we can get some precise numbers. Okay, so now you can see, so I'll make a little table over here and I'll say, now this is going to be a second order fit. Okay, and so when we were doing the first order fit, we got best fit coefficients B0 and B1. In the second order fit, we've got B0, B1, and B2. And I can copy those numbers down here from the graph. So the intercept is going to be B0. That's going to be, oops, that's going to be this number down here, the 0.99 number. So I'll just copy and paste the number up here. B1, this is the coefficient that multiplies the pressure to the first power. So that's going to be this number right here that is multiplied by x. So negative 1.7 times 10 to the minus 3. That's going to be the B1 virial coefficient. So I'll copy that number. Command C, Command V, copy paste. And the second virial coefficient, that's the coefficient of the pressure squared. So I'll select that number, copy, and paste it over here. So now I got my best fit parameters. Yeah, that basically completes this part of the exercise. Maybe I'll go ahead and I'll also compute the fitted value of the compressibility according to the second order model. So basically, we're going to calculate this equation for these pressure values where we measured the compressibility at. So according to the equation, we want the second order virial coefficient times the pressure squared. So the first pressure is this guy here, and I'm going to raise that to the power of 2. Plus, we want the B1 coefficient times the pressure to the first power. Plus, we're going to take the B0 coefficient, and that doesn't get multiplied by anything. Okay, and then I'm going to want to drag this formula down to compute the compressibility for every single one of these pressures. And so the fastest way to do that, so that I don't have to type the equation 6 times, is to make use of static versus non-static cell references that we talked about last time. So I'm going to make the references to each one of these virial coefficient parameters a static reference. So I'm going to put dollar signs here in front of the I and the 4, right? For the B2 coefficient, I'm going to put dollar signs in front of I3 for the B1 coefficient and in front of I and 2 for the B0 coefficient. So now these are static references, but the reference to the pressure over here is a non-static reference. So now if I hit enter, I get a value. I can take this equation, grab the lower left side of the, or I'm sorry, the lower right corner of the cell, drag it down, and that should drag down the formula, and it should update properly so that it always refers to the proper pressure, right? When you drag the formula down, the non-static reference should also get dragged down. So now I'm calculating the compressibility for each different pressure measurement. Okay, and you can see these values are in pretty good agreement with these values. So it looks like we did it correctly. It makes sense. Okay, so that was example 10. Let me quickly minimize this and I'll go back to the PowerPoint. Okay, so we got the coefficients, right? But whenever we measure values in the lab, we don't want to just report the values. We also want to report the uncertainty. So we also need to start talking about how do we deal with uncertainty when we're talking about nonlinear fits. So there is a figure of merit for how good your fit is, and that's called the standard deviation of regression. This looks a lot like the equation that you saw for standard deviations, but in this case, you take the measured y value minus the y value that's predicted by the fit for each value of x, right? So this is the residual. You take the residual for each data point that you measured and square it. You sum the squares of the residuals, and then you divide by the degrees of freedom. And then finally, you take the square root. Okay, and that's the definition of the standard deviation of regression, right? So if your residuals are large, right, then your fit is not very good. The data is going to be far away from the best fit line. You're going to have a large value of sigma. If your fit goes really close to all the data points, then these residuals are going to have a small magnitude, and you're going to have a small standard deviation of regression. Okay, and the number of degrees of freedom depends on what type of an equation you're fitting your data to. Because the number of degrees of freedom, in this case, is going to be the total number of measurements minus the number of fit parameters that you're including in your fit. Okay, because, you know, let's say if you're fitting to a line, you need at least 2 data points to determine a line, right? The slope and the intercept of the line. And you'd need at least a 3rd data point to be able to say anything about how good your fit is, right? What's the uncertainty? How far is the 3rd point away from the prediction? If you're fitting to a quadratic, you know, a quadratic can always go through 3 data points, right? So you need at least a 4th data point in order to be able to say anything about how far away that data point is from the prediction of the quadratic that was made by fitting the other data points. So that's why, you know, for a quadratic, you would take the total number of data points and you would subtract 3, because there's 3 fit parameters that are required to fit a quadratic. Okay. Okay, so let's go on to the next example. So the next example says, now we're going to calculate the standard deviation of regression for the fits of the compressibility data from the linear fit and from the 2nd order polynomial fit. Okay, and then we can see that the 2nd order polynomial provides a better overall fit to the data than the linear fit. Okay, so let me, I'll go to the slide so that we can see the equation, and I'll minimize here and I'll go back to my spreadsheet. Okay, this time I will drag this over a little bit so that we can see the equation while we're working. Okay, and so yeah, we're going to want to calculate sigma for our linear first order fit and for our quadratic second order fit. So the first thing that we need to do is we need to calculate the residuals, right? So the residual is the measured y value minus the predicted y value. So for the linear fit, that would be, so I'll label this residual, or actually maybe I'll go ahead and calculate the square of the residual. So I'll call this column r squared. And so for each of the measured data points, I'm going to make this a formula, and it's going to be equal to the measured compressibility minus the compressibility that we got from the fit, and I will square that. Okay, and so now I can take this formula and drag it down, and I should get each respective residual squared. And so I've got y minus y predicted squared for each data point. So the next thing, according to this formula, that we need to do is sum up the squares of the residuals. So I'll take the sum of the squares of the residuals. So I'll use the built-in sum function, and I'll select these 6 r squared values to add them together. Next, we need to divide by the number of degrees of freedom. So for this fit, the number of degrees of freedom, okay, so this is a linear fit. So how many fit parameters? 2, right? And the total number of data points was 6. So the degrees of freedom is going to be 6 minus 2. Okay, so 4 degrees of freedom. And so now I think I'm ready to calculate this formula. So sigma, right, the standard deviation of regression is going to be, I'm going to take the sum of the squares of the residuals, that's this cell here, divide by the number of degrees of freedom, nu, that is this cell here, 4. Oops, I need to take this one, divide by this one. And then I take all that and take the square root of it. So I'm going to put parentheses around this expression, and I'm going to type sqrt, that's the name of the square root function. Okay, and I hit enter, and that tells me that my standard deviation of regression in this case is 0.013. Okay, now for the second order fit, we're going to do the same thing. In order to save time, I can do a little trick, which is if I make the reference to the experimental value a static reference, or at least if I make the so if I just put a $sign in front of the B, that means that when I copy this formula over to another column, left or right, it's going to keep the reference to the same column, but if I drag it up or down, it's not going to hold the number static, right? So the row is going to change if I drag it up or down, but the column will not change. So if I put a $sign here and enter, then now I can copy this formula over here, and it should copy over correctly because now the B column is static, the other value is not static. And now, oops, okay, so for some reason, the number format is a little strange. So maybe I'll just change it. So I'll tell it I want a scientific. Okay, so for some reason it's wanting to display 18 decimal places. That's a bit extreme. So maybe just 4 decimal places is enough for us. Okay, now it looks like a reasonable number. So now I can drag the formula down and we can see that it worked. I get the square of each residual and the references look correct. Okay, so I can also copy over this formula and it should copy over in the correct way. I'll label this column here. This is the residual squared. And I'll just check that the reference copied over correctly. It looks like I'm taking the sum of the correct range of data. Okay, so now the number of degrees of freedom is going to be less because we have more fit parameters. So we have 6 data points, but now in the quadratic fit, we have 1, 2, 3 fit parameters. So the number of degrees of freedom is 6 minus 3, which is going to be 3. So number of points minus 3 fit parameters. Okay, and then finally, we're ready to calculate sigma. Instead of copying this formula again, I'm just gonna copy and paste from over here. And you can see that if you're smart about the way that you organize your spreadsheet, you can save a lot of time by just copying over formulas and making sure that the references copy over correctly. So now I'm taking K9 over K10 and taking the square root of that. So that's the correct formula, right? We want the sum of the squares of the residual divided by the degrees of freedom, and then we want to take the square root. Okay, so which fit is overall better? Which one goes closer to the data points? You can see by comparing the sigmas. The first fit, the linear fit, has a standard deviation of 0.013. The quadratic fit has a sigma of 0.006. The sigma for the quadratic fit is smaller. That means the quadratic fit more closely represents the data. It goes closer to each data point. Okay, any questions? Okay, let me start my presentation one more time. Okay, so we finished example 11. So the next example or the next topic is, it turns out, if you include more fit parameters, you can almost always get a better fit to your data, right? If you give your model more flexibility, you can get your fitting curve to go right through all the data points. But sometimes it makes sense to include more parameters. Sometimes it doesn't make sense to include more parameters because the data that we measure in the lab always has noise associated with it. And so you don't want a fit that's so flexible that it's just, bending around to go through all of the noise, right? You want it to go through the general shape of the data, not, fitting the noise, right? So in other words, in this cartoon that I showed you at the beginning, if your data looks like this, you might not be justified in using a fit that looks like this to really try to go through every single data point. Okay, so you might, if you had a data set like this, you might ask, how many virial coefficients are we justified in reporting, right? So we've reported 3 virial coefficients. Would it make sense to report also to try to report a 4th virial coefficient? Okay, and so an objective test that you can use to see whether you are statistically justified in adding another parameter to your fit model is called the F-test. And you're going to need to use the F-test on one of your lab reports this semester. So let's talk about this. Okay, so this is a statistical test for determining whether you should include another parameter in a fit model. And it's based on a statistical parameter called the reduced chi-squared parameter. So this reduced chi-squared parameter, if you compare this equation to the one on the previous slide, it's just the square of the standard deviation of regression, right? It's the same equation as this one, just without the square root over here, right? Yeah, and it looks a lot like, if you remember, the definition of chi-squared is just the sum of the squares of all the residuals without this 1 over nu. So the difference between chi-squared and reduced chi-squared is that the reduced chi-squared parameter gets divided by the number of degrees of freedom. Okay, and it's denoted chi sub nu, right? So the subscript nu means it's the reduced chi-squared, not the regular chi-squared. Okay, and here, of course, nu is the number of degrees of freedom, right? The number of data points that you measured minus the number of fit parameters. Okay, so in order to perform the F-test, right? So let's say, in our situation, we've done a quadratic fit. We want to decide, should we do a cubic fit, right? Should we include one more fit parameter? So in order to decide that, you can consider both of these models, and you can compute this parameter called the F parameter and perform an F test. And so basically, okay, what does this F mean? So the F parameter has two arguments in parentheses. The first argument means when you're comparing two fits, how many parameters are you adding when you go from one to the next? And so for our purposes now, or actually in 3108 in general, we're only going to consider adding one parameter at a time. So this first number should always be 1. And then the second number is the number of degrees of freedom in the fit that has more parameters in it. Okay, and by definition, the F test is given by this equation here. So you take the number of degrees of freedom for, in our case, the quadratic fit, and multiply by the reduced chi-squared value for the quadratic fit. Then you're going to subtract the number of degrees of freedom in the cubic fit, right? So the fit that has more fit parameters, so lower, smaller number of degrees of freedom, times the reduced chi-squared value for the second fit, right? The one that has more fit parameters, divided by the reduced chi for the second fit. Okay, and after you've calculated this value, you can compare it to a number in a table, and I'll show you how to do this. And you can use this to decide whether you are justified at the 95% confidence level in including another fit parameter. So you're going to use the equation. You can find it in your lab manual. It's labeled equation 48, but it's this equation right here to calculate the F parameter. Then you're going to compare the observed value of F that you calculated from your data to one that you're going to look up in a table. And I'll show you that table in just a second. And if the observed F value is greater than the limiting F value that you look up in the table, then model 2 is going to be preferred over model 1, right? So including the extra parameter is going to be statistically justified. If the F value is less than the limiting F value, then even though you get a smaller value of sigma, right, your fit is better, you probably shouldn't include that extra parameter because it's not it's not really statistically justified by the data. Okay, so the table that you can look up these F values in is shown here. This is the table that's in your lab manual. It's table E1, so it's in Appendix E of Chapter 1. And let me move this so that my mouse works better. Okay, so the column that you need is this last column. This tells you the limiting value of F at the 95% confidence level. And so, let's say if your second fit model had 3 degrees of freedom, then you would want to use F 1, 3. So you would use this value here. Okay? Okay, so now next we're going to do an example where we perform an F test. So we're going to use the F test to show that the second order polynomial provides a statistically better fit of the compressibility data than the first order polynomial. But we're going to see that it is not necessary to perform a cubic third order polynomial fit. Okay, so let me exit the PowerPoint. I will go to this slide that has the equation that we're going to use to calculate F. And let me make this a little bit smaller. Okay, I think that's still big enough for you to see. Okay, I'm going to go back to my spreadsheet. And now we're going to calculate these F values that we need. Okay, so I think we have everything that we need. Okay, so over here, here's the second order fit. We're trying to decide, is the second order fit, statistically better than the first order fit? So we're going to do an F test comparing the first order and the second order fit. So I'll put that down here. So let me calculate. This is going to be F 1, and then the number of degrees of freedom in the fit with more parameters is 3. So this is going to be the f1 comma 3 value. And I'm going to calculate it according to this equation here. You can use either the left-hand side here or the right-hand side here. It doesn't matter which one you use. I'll use this one. So according to this equation, I want the number of degrees of freedom in fit 1, which is this one. So 4 times, oh, I'm sorry, I forgot to calculate the reduced chi-square value. I'm going to need that first. So I got ahead of myself. So first, let's calculate the reduced chi-square value for both of these fits. And then we have all the parameters that we need to evaluate this equation. So let me go up one slide higher to this one. So here's the definition of reduced chi-squared. And you can see it's really just the square of the sigma parameter that we already calculated. So the reduced chi-square for this first fit is just going to equal this value squared. And for this second fit, we're going to take this value of sigma and square it. Okay, and that gives us the reduced chi-squared. Okay, so now I have everything I need to calculate f1 comma 3. And I'm going to do that. Let me go to the formula so that you can see. So here's the formula. I'll just enter it here. So we need number of degrees of freedom in fit 1 times the reduced chi-square value for fit 1, right? Minus number of degrees of freedom in fit 2. That's going to be this number here, 3, times the reduced chi-square value for fit number 2. And then this whole thing I want to divide by the reduced chi-square value for fit number 2. So I'm going to put parentheses around this expression that we created and divide the whole thing by the reduced chi-square value for fit 2. Okay? And that should give me the f1,3 parameter. So this is the observed f1,3 parameter that we get from our data. And now we have to compare this to the value from the table. And if this value is greater than the one in the table, then we're justified in adding another parameter to our fit. So the value that we get from the table is, let me make this a little larger so you can see it. Okay, so we have 3 degrees of freedom in the second fit. So we want f1 comma 3. So we're going to go down to the third row of this table here, and we see that the f1,3 value is 10.13. So I'm going to, whoops, sorry. I'm going to enter that into my spreadsheet over here. Oops. Not letting me grab the right place, doesn't matter. Okay, it should be 10.13. Okay, and now we can see 13.2 is greater than 10.13, so we should include the extra B2 coefficient in our fit. Okay, but what about the B3 coefficient? Can we measure that with statistical significance from this data set? Okay, so let's try. So I'm going to go over here and we'll try with a third order fit. So I will go over here. I'll say this is the third order fit. And so in the third order fit, I'm going to end up with a B0, B1, B2, and a B3 because I'm going to include the cubic term in the quadratic. Okay, and then, so okay, the first thing I'll do is I will just copy the second order fit. Actually, let me make this bigger because we don't need the PowerPoint right now. Okay, so now I have a full window. Okay, so I'll take the second order fit graph, I'll copy it, I'll click in an empty cell and then paste. Okay, and I'll change the title. This is going to be the third order fit. And the fastest way to go from the second order fit to the third order fit is just to right click the trend line, go to format trend line, and I'll just change the polynomial order on this graph from 2 to 3. And then you can see that the equation that's printed here on the graph updates automatically, and also the trend line updates automatically. Okay, so, oops. Okay, so here's my new fit equation. And now you can kind of see, I mean, if you look at what this fit looks like, it's kind of got a one curvature over here, and then it like curves around, it changes its concavity to try to fit this point over here. So this might be an indication, just visually looking at this, that maybe we've included too many fit parameters and it's sort of contorting itself in order to try to fit all the noise in the data. Okay, but we're going to apply the F-test because we want a more objective way of determining whether we should include this parameter or not. And so I'm going to do exactly what we did over here. I'm going to create a column called Z fit, and I'm going to calculate the fit for the third order in the third order case. So here we have the B0 coefficient is this number right here. The B1 coefficient multiplies x to the first power. So it's this number here. I'll just copy and paste. The B2 coefficient multiplies pressure squared. So I'm going to select that number, copy, paste. And wait a minute, that didn't work. That's the wrong number. Let me try that again. Okay, I'm going to select this number, copy, and paste. Okay, somehow it doesn't work. I'll just type it 9.501. That's enough significant figures times 10 to the minus 6. Okay, and then finally, the B3 coefficient. Okay, that one copies. No, that also didn't copy correctly. I don't know why it's not working. Okay, minus 2.3953 times 10 to the minus 8. Okay, so now I can calculate Z fit, but actually I can just take these numbers over here, and because I did this in, oh no, I can't do that. Okay. Yeah, no, I need to write another equation. Okay, so I'll just copy this equation basically. So we need the B3 coefficient times the pressure cubed plus the B2 coefficient, and I'll make the references to the coefficients static references. Times the pressure squared plus the B1 coefficient times the pressure to the first power plus the B0 coefficient. Okay, so now I think this equation's correct. I'll hit enter. And I think I can drag it down and calculate all these values. And now it looks correct, right? Down here, we get 0.75. That agrees with the experimental value. Up here, we get a number very close to 1. Looks right, looks reasonable. Okay, so now I think I can take this column of numbers here and just copy it over. And I believe it's set up in such a way that the references should copy over correctly, right? So we get the residual, right? Z experiment minus Z fit squared. And looks like the references are correct. So now I have a list of residual squared. I'm going to copy over this formula here to take the sum of the squares of the residuals. Now the number of degrees of freedom is going to be less, right? Because now we have 4 fit parameters. So now the number of degrees of freedom is 6 data points minus 4 fit parameters. So it's only 2. Okay, the equation for sigma, I'm pretty sure I can just copy over. It's just this number divided by this number, and then you take the square root. The reduced chi-squared, I believe I can also copy over that formula because it's just the sigma value squared. And now, instead of F1 comma 3, now the number of degrees of freedom in the second fit, in the most recent fit, is 2. So I'm going to change this to F1 2. But I think I can copy the formula over because I arranged this table in a way that everything is arranged in sort of a symmetrical way. So let me just check that I'm taking the right numbers, right? So we want the degrees of freedom in the previous fit times the reduced chi-squared value of the previous fit minus the degrees of freedom in the new fit times the reduced chi-squared value in the new fit. And then that whole formula gets divided by the reduced chi-square for the new fit. So I believe this formula is correct. So that says my F12 value is now 2. So now in order to see whether we should include this B3 parameter or not, we can go to the table over here. And so now we only have 2 degrees of freedom. So we need to look at the second row of this table here. And this tells you that the limiting value of the F parameter in this case should be 18.5. So I'm going to go over here and enter. So maybe I should have labeled this. So I can call this F13, for the 95% confidence limit. And then over here, it's going to be F12 at the 95% confidence limit. And what did I say that number was? 18 point something, 18.5. Okay, so now the F value that we got is significantly less than the limiting F value from the table. And so that result would tell you that you should not include the third order fit parameter. Okay, any questions about that? Okay, I will go again back to the PowerPoint. Okay, so we're finished with example 12. Okay, so we've talked about applying statistics to the fit model to decide which fit model we want to use. And we've gotten virial coefficients, but so far, we've only gotten coefficients. We don't know what the uncertainty is in those coefficients. So the final topic in this section is how to get the 95% confidence interval in the fit parameters that you obtain from a polynomial fit in a spreadsheet. Okay, so last time we talked about linear fitting, and we used this function linest to get the standard deviations in the parameters, which we then use to calculate the 95% confidence intervals. You can also use linest with a polynomial fit. You just have to add information about which polynomial terms you want to include. So in order to make this work, I think in the recent versions of Excel, you don't actually have to select a 3 by P area. You can just select one cell and type this formula and hit enter. It should work. So you want to type equals linest and then open parentheses. Then it's going to ask you to select the known y values. And then after that, you select the known x values. But after selecting the known x values, you want to add some more information. So you need to tell it that you want those x values to be raised to the power of 1, 2, 3, 4, etc. Whichever polynomial terms you want to include. You need to put here, right? So these polynomial powers need to be put inside of curly brackets. And then it's going to ask you whether you want to calculate the y-intercept in the normal way, and you say yes, true. And then it's going to ask whether you want to return, whether you want the output to include additional fit statistics, and you want to enter true. Okay, so let's try that. So, and then here's what the output looks like. We'll look at an example in just a second. Okay, so I put the answer on the slide. I forgot to make this a animation. Oh, well, it doesn't matter. Anyway, so the next example is we're going to use the linest function in Excel to obtain uncertainties in the parameters from the second order fit and from the third order fit. And then if we do it correctly, the answer should agree with what I calculated this afternoon. Okay, so let me bring up the spreadsheet again. Okay, so I will take these graphs and put them down here so that we have room to work. Okay, so for the linear fit, I can put my linest function here. So for the sake of completeness, we can just do all three. So First, it wants the known Y values. That's the measured compressibility factors. Next, it wants the known X values. That's the pressures. Then it wants, we want to calculate B normally. I can either type true or I can enter 1. And I'll enter 1 again because we want to return additional regression statistics. So I'll close the parentheses, enter, and here's the output. And remember, the first row is the value of the fit parameters, right, which should agree with these parameters that we calculated up here. The second row is the standard deviation in the fit parameters. That's what we're going to use to calculate the 95% confidence interval. And then the third row, this looks like it's the R squared value. So this one's R squared. And then the next cell here, this looks like it's the sigma. And then this stuff down here, you don't really need. That's just some extra parameters. Okay, but we can go ahead and calculate the 95% confidence interval. So I'll put that down here. So 95% confidence interval for the linear fit. So the 95% confidence interval, remember the formula is you take the standard deviation times the student t-factor and divide by the square root of the number of measurements. So we're going to take standard deviation times the student t-factor, which we have to look up in a table. So actually, I need my PowerPoint again. So let's go back to the earlier slide where we had this table of student t-factors. So in the linear fit, the number of degrees of freedom is 4. So the appropriate student t-factor is 2.78. So over here, I'm going to type standard deviation times 2.78, divide by the square root of the number of measurements, which is 6. Okay, and then I can, I'll make this one a static reference to the number 6. And then I should be able to just drag over this formula. And now it should calculate 95% confidence interval for the B0 parameter. Okay, and now I can work with the second order fit and the third order fit. So in the second order fit, now I need to use the special version of LineNest where I tell it which polynomial terms to include. So first I tell it the known Y values, that's these ones here. Then I tell it what are the X values, that's this range here. And now, according to what it said in the PowerPoint, we need to raise it to the power of, in this case, it's a quadratic second order fit. So we raise X to the power of 1 and 2. So I type 1 comma 2. I close my bracket. And now I'm going to type 1 comma 1 and enter. And now I get, instead of 2 columns of output, I get 3 columns of output because now there are 3 fit parameters. And I think I need one more space here so I can label these. So, you know, if we just compare these numbers to these ones, we can see this one is B0 and this one is B1. Okay, and then over here, it looks like this one is B0. This second one corresponds to B1. And this one on the left corresponds to B2. So it actually puts the parameters in the same order as they appear in this equation. Okay, not necessarily in the same order as what we had in our lab manual. Okay, so then finally over here for the third order fit, I'm going to do LineNest, and the known Y values again are these ones. The known X values are these ones. We have to, in this case, we raise it to the power of 1, 2, and 3 because we're including you know, coefficients of X, X squared, and X cubed in our fit. And then I type 1 comma 1 and enter. And now we've got the LineNest results for the third order fit. And just labeling the columns again. Now we have B3, 2, 1, and 0. Okay, and then finally I need to calculate the 95% confidence intervals for each of these parameters so that we can put our final answer that we're going to report, you know, into the lab report. So for the quadratic fit, the number of degrees of freedom is 3. And so the appropriate student T factor is going to be 3.18. So the formula is going to be you take the standard deviation, which is the second row here, times, what did I say, 3.18? 3.18 divide by square root of 6. Okay, and I'll copy this formula over. That should work correctly. And then over here, we only have 2 degrees of freedom. So over here, the student T parameter that we're going to use is going to be 4.3. So here, I'm going to say, I'm going to take the standard deviation of each parameter times 4.3 and divide by the square root of the number of measurements. And I'll drag that formula over, and I believe that should be now correct. Okay, so how would we report these final parameters? So usually we round the uncertainty to just one significant figure, and then we report the fitted parameter that we've obtained to the decimal place that contains the uncertainty. So in this case, the uncertainty, so let me just write this on the board. So from the second order fit, we would say the B naught coefficient is going to equal, I'm sorry, it's this one here, right? So the uncertainty is going to be 0.006, so we're going to report 3 decimal places. So 0.990 plus or minus 0.005. Okay, and the B naught coefficient, remember, is unitless because the compressibility factor is unitless, and the y-intercept should have the same units as the compressibility factor, right? It should have the same units as the y-axis. Okay, the B1 coefficient that we get, so in this case, the uncertainty is going to be rounded to 2 times 10 to the minus 4. So it's going to be 0.0002. That means we want to round this number to the thousandths place. So we're going to report this number as negative 0.0017. So this number is going to be negative 0.0017 plus or minus 0.0002. Okay, and then the B2 coefficient finally. Okay, this has some, very small order of magnitude. So probably we're going to want to report this in units of, times 10 to the minus 6. Oh, and I forgot to write the units on this number, right? This coefficient gets multiplied by pressure, and this number times pressure has to give a unitless compressibility. So this has to have units of reciprocal pressure. So it's atmosphere to the minus 1. Okay, and then finally over here, we have an uncertainty of 9 times 10 to the minus 7, which is the same thing as 0.9 times 10 to the minus 6. So the uncertainty is going to be 0.9 times 10 to the minus 6. And so then we're going to round this number to the 10 to the minus 7 place. So we're going to round this number to 2.6. And this number gets multiplied by pressure squared to give a final value that has units of, that's unitless. So it has to have units of atmosphere to the minus 2. Okay, does that make sense? Okay, and then, for the sake of anyone that's watching this video in a month's time, you probably couldn't see the board, but I'll just put up the numbers, how you should report them. Which should look like that. Okay. Okay, and so, if you report the numbers from the third order fit, this is what you should get down here. And one thing to notice, so, for the B naught, B1, and B2, oh, I'm sorry, this should be atmosphere to the -3 down here. So this one down here should say atmosphere to the -3. That's a typo. So, these first two coefficients have parameter values that are larger than the reported uncertainty. That's usually the case. But notice that, the B2 parameter is only barely larger than the uncertainty in the B2 parameter. And the B3 parameter that we got is actually smaller than the uncertainty in B3. So what that tells you is that B3 is so small that you would need a lot more data in order to really be able to measure that. So with this much, with the data set that we had with only these 6 data points, we can't really say that B3 is statistically different than 0. So in other words, we should set it to 0 and not include the B3 term. We should only go up to second order. Okay, any questions about that? Okay, so that takes us to today's Blackboard quiz. Before I do the Blackboard quiz, I'll just review the first Blackboard quiz. What were the answers? So which quantity should you use in PChem lab to express uncertainty in a measurement? Whoops. Right, not standard deviation, but 95% confidence interval, right? Okay, and then when you multiply two experimentally measured values, how are the errors propagated? Remember, when you add or subtract, the errors get added in quadrature. When you multiply or divide, the relative errors get added in quadrature, right? So the error divided by the value gets added in quadrature. Okay, so that means it follows this formula. So delta Q, if Q equals X times Y, then delta Q over Q best equals, delta X over X best added in quadrature to delta Y over Y best. Okay. All right, so now I will pause the video.